Thank you for the invitation, and not only for the invitation, but I think, for the effort in putting together these series of seminars. I applaud these efforts. I think it's so much needed for the community. So thank you, Oscar. Thank you, Tiago. And if you need help with anything, just let me know. So today I'm going to be talking about neuroscience-based interaction in healthcare. I will present kind of the latest results from my lab. Some of part of this work is not published yet; it's under review, so be gentle there. And I want you to help me I have to promote interactivity during the talk. I will be using a slider, so if you please have your phone at handy to scan that QR code or join a Slido with that code to answer the questions, please. You will find this information later on if you cannot catch it at the moment. So yes, like Oscar was saying, I would like to start at the talk talking a little bit more about where I work, where it's ICESE, and my context. So I work in the computer science at ICESE. ICESE, like Oscar said, is a research center that only has graduate programs. So we do have a master program and a PhD program, and it is located in Ensenada. And you can see in the photograph, this is the view of the campus. We do have ocean view, so it's very beautiful. And it is located like 1.5 driving distance from San Diego, California. So we do have a lot of relationships and collaborations with California because we are super close. I think we are closer to them than the other parts in Mexico. The department where I work, it's very traditional computer science. The areas that we have is computer vision, parallel computing, and bioinformatics, data science, and of course you become an HCI. And the good thing about our program is that it's a very prestigious program in Mexico and Latin America. I really do not know internationally, but the good thing is that it's very hard to get into the program, but once you get in, all enrolled students receive a full-time scholarship so they can focus entirely on their research. The other thing I'm very passionate about this year is You Become Easy 2023. I'm co-organizing it with Nadir Weibel, which is the researcher in San Diego, UCSD San Diego, and Christoph Walderhoven, who works in Germany. And we put together this bid, and I think it's a huge milestone for this community because it is the first time ever that You Become happens in Latin America and also in Mexico. And of course, we picked up Cancun. So yay! So right now, I think it's just an invitation for you to go to the link youbecome.org and see all the opportunities that we have for you to come. We do have some programs for that has travel subsistence, so you can still apply for those. And of course, there are other academic opportunities still to send your work. Oscar currently has a workshop in digital therapeutics. Deadline is June 15th. So if you would like to send some work and present it at the conference, you still have that opportunity open. So I invite you to send that, and hopefully I can see you in Cancun and we can have like a super awesome time there. The other thing that I'm currently doing, I'm actively, most of my time goes into this network. So I'm working right now in this series network that works in developing technologies for accessible education. This network was put together by Jillian Hayes and Candy Augers from UC Irvine, and they downloaded a huge amount of money from the Robert Wood Johnson Foundation to put together this network. And as you can see in the map, in the network, there's a lot of researchers for several very prestigious international institutions like University of Cambridge or Carnegie Mellon, University of Washington, University of California. And the idea is to have collaborative projects and partnerships between these institutions. and then kind of create like a spin-off from the results of research into companies, and kind of create this model that from the revenue from the companies support projects, research projects, and then put the money back. So the funding is for 5 years, and the network is super amazing. They have very driven and talented and committed researchers, and I'm happy. So I'm doing a lot of work now in education and accessibility, and I will also like to thank Robert Wood Johnson and the series for the financial support. I will be presenting some of the results today. Okay, so for today's work talk, what I would like to do is first I'm going to start motivating the problem from a healthcare perspective, and then I will dive into this concept of neuroscience-based interaction, and then I will showcase through 3 research projects this concept and what I mean by neuroscience-based interaction, and then I will close with takeaways. So please, like I said, help me to scan the code or go to Slido and answer this question for me. Do you have free access to healthcare? Wow. Yes. Okay. And that's kind of surprising. So in Mexico, we do have we have access to healthcare. It is partial. We need to pay for our own salary, and half of it is subsidized by the government. So yeah, that's what I'm expecting more. And so for those that have used or have public healthcare, or you might have a perception of somebody who has used public healthcare, how would you rate your experience of using these healthcare services? 4. Wow. You guys have an awesome healthcare service. 5. Okay. Yeah, of course, it's Europe. 3. Now we're talking. So I've been giving this talk at several places. So in Mexico, we do not have very good experience of the public healthcare services. So most of the people, in Mexico or developing countries will go for 1 to 2 or 0 rate. And so we ended up paying a private health insurance. And the problem is basically because we don't have public healthcare services, and the healthcare services are very poor. And one of the reasons is that there's a shortage of specialists, lack of resources, lack of training. So there is no a very good healthcare system. So the dream is, well, you guys feel like living in a dream, but the dream is that how can we make technology to have accessible healthcare system in developing countries, right? And this is a dream that's been there before, like the Theranos kind of company. And we have that dream too as well, but we would like to do that not by not going to jail or lying to people, right? So I think the pervasive healthcare community has made a very nice, compelling argument that we can do something along those lines. I think the community has reached a point of maturity in which we do have very nice examples of how can we take healthcare services into our home by monitoring our body and then sharing this information with us. Like, for example, activity trackers, sleeping trackers, those are technology that are very robust and we are using in our everyday lives at this point. So the way that I see pervasive healthcare, and of course there are other options, but motivating like that in the talk, is like we would like to know what is going on inside our body. So we are using a lot of wearable sensing devices, or we're using what we're integrating or putting sensors into the environment so they can monitor what is going on in our health. And kind of like a car, we want to know what is happening in our heart or a activity, and then use like the mobile phone and the smartwatch as a kind of advisor to understand what's going on inside our body. And we are working in developing this app that shows a bunch of multimodal stream data that talks about what's going on in our body and is trying to make us like more aware or more engaged of what is going on with our health. And we even got into the point that we have developed this type of technologies for even babies that I think that are more the most vulnerable population alive. But the problem that I think we can see, like, you know, the way we're interacting with the technology is kind of changing. So we can see kind of these environments in which children or babies or individuals are saturated by technology, and they are interacting with this type of technology. The problem that I see here, and you can see in this example, this is a child that is attending to a remote class, like during the COVID pandemic. And the problem it is that we are changing the way our brain is connecting by accessing the digital services like that. So this child he's seeing his teacher in front of him, but the teacher is not actually there. It's just a digital image of it, but he's interacting with it, and that creates a different neural path in their brain, different than having the person in front of you, like having a more organically kind of interaction. And I think we should be very, you know, take responsibility of the type of the technology that we are creating and how that affects our brain. So we are creating this stimuli that is mostly digital. It could be like a touch-based interaction interface, like a tablet or a video game or something else, or sensor attached that affects our brain. It is affecting how our senses perceive the environment. And now we not only have the organic environment, now we have also the digital environment, and they are both integrated into the fabric of our everyday life, like Weiser said. And now we do have these environments, and that changes the neural paths that we are creating. So yes, the new generations, the brain, it is connected differently, in that has implications in our health and in our development. So the way we create this stimuli, it elicits reactions, experiences, or memories, alters our perceptions, and creating concepts, because we do have both environments. So what we are kind of doing here is we are rewriting the sensory processing system. So we have like the body's natural sensory processing system, and we perceive a stimuli through our senses or our sensory receptors, and that stimuli is no longer organic. So we do have big data now, and we have novel interactive interfaces with covered or saturated with multimodal digital stimuli. And then the sensory receptors in our work pass these information along the nerves, which will be the kind of the equivalent of what sensors are currently doing. And then the neurons transform the sensory information into electrical signs, which is kind of what the code does, right? So we have an API, and we have access to these raw data. And then these electrical signals move through the synapses and the synapses in our brain. And it's kind of like navigates the entire nervous system. So it's similar what the cloud does for us, that helps us navigate data, helps us navigate services or access different services. And then finally, it reaches our brain, and the brain is kind of responsible for organizing this information, eliciting a response, and is what's going on with reasoning algorithms in artificial intelligence or machine learning. So we are kind of creating the same backbone that we have in sensory processing in our body, but it's different. It's a digital stimuli, and it does have an effect in our brain. So that's the entire idea of neuroscience-based interaction. It's not something that is defined there. It's something that I would like to highlight. There's a lot of technology that is being developed along these lines, But I would like to highlight as a field or as a concept that we need to take more discipline in understanding the scientific study of how HCI or the technology that we are creating affects our brain. Neuroscience-based interaction also focuses on the design and use of natural user interfaces to create and direct communication between our brain or innovative interactions using digital stimuli. And it's an area of HCI that uses methods or techniques from neuroscience, cognitive science, and computer science. So to help you to understand more of these concepts, today I will showcase 3 examples of research projects in healthcare that use neuroscience-based interaction. The first 2 I'm going to talk about are more related to support the care and early detection of children with autism, and the final one is more in the rehabilitation realm. The first project, of course, the more natural kind of paradigmatic example of a neuroscience-based interaction is to use brain-computer interfaces as an input to control video games. So I'm going to start with that project. So autism is a neurodevelopmental disorder that affects 1 out of 54 children. And it impacts social interaction and behavior. The problem with autism are twofold. First of all, the diagnosis is currently delayed, so early intervention is very limited. And the most interesting or the goal is to have early intervention at time so we can intervene and help the children to develop typically. The problem of these both things, treatment and diagnosis, is accessibility to healthcare services. So there's a shortage of specialists, and for those that do have access to healthcare is very costly. So most of the therapies run for 40 hours a week, and they are super costly, and so it's difficult to access this kind of services. So one of those treatments that has been very successful, and it's not a pharmacological treatment, is neurofeedback. Neurofeedback is a type of training or therapy that teaches self-control of brain functions. And what it does is we use, like as you can see in the images, the neurologists or neuropsychologists, they use a cap saturated with electrodes that measure our brain waves and then gives us feedback in the form of both audio or video feedback of what is going on in our brain. And it's for us to find like something to self-regulate those brain waves according to a threshold defined by a therapist. Usually the audio and video feedback that neurologists use are movies or cartoons, to be honest, because there are some games that come with the kit, with a cat, but they don't find them like very engaging, and they find it like they help individuals to work other areas of the brain. So what we were trying to do here, and also neurofeedback has shown promising clinical results, improving attention problems for children with autism. It has been even compared against pharmacological treatment, and it has shown that neurofeedback has better results, both short term and also in long term. And the problem that it has is that it's very expensive. So you have to do 40 hours a week, and one session costs around $80. And the other problem is that it's not very engaging. So neurologists and neuropsychologists, they don't have tools to properly showing what is going on in our brain, and having the raw signal is something that users do not understand. So we think that here video games can help a little bit with children. So beyond the cap, there are other options that have emerged recently. There are a bunch of AI headsets. We review the Muse interaction and the APOC and also the Mindwave Neurosky that use the 2020 standard to know where to place the electrodes. The difference between these headsets is the amount of electrodes they use. And we ended up choosing the mind wave from Neuroscience, which has one electrode in the front. And in the front of the brain, you measure executive functioning. In particular, this headset claims to measure attention and emotion. So it has one electrode and one reference clip to avoid noise. To be honest, we did like better the music interaction headset, but the diameter of the headset did not fit the diameter of the heads of children. So we ended up going with Mindwave from Neuroscience. So we asked ourselves, can children with autism use their attention and measure with a BCI headset to control a neurofeedback game? So we follow a methodology, a user-centered design methodology. So we work very closely with neurologists, psychologists, children with autism, parents with autism, and so on. HCI experts, and you become experts as well. And we ended up developing this game that we call Farmer Keeper. Farmer Keeper is, the narrative of the game is that it happened a storm, and the storm scared all the animals in the farm, and they are scattered throughout the farm. They went out their pens, and so a farmer needs to find them and get them back to their pens safely. So the game is a runner type of game. So whenever the child is focused or is putting attention according to a threshold predefined by a therapist, the runner will start running, the farmer will start running and catching all the animals that he finds in the path. And if he stops staying focused, then the farmer will stop. Let's see a video of how this game works in practice. So as you can see on the left, you will see a child with autism using the headset and the game. And on the right, on the bottom, you can see the raw signal of the electrode, and then how the headset converts this raw signal into units of attention. And based on the threshold defined by the therapist is how the farmer runs. Oh, I'm sorry. So as you can see there, it's on green, so the child's paying attention and the runner is running. So there's an instance when the child stops paying attention and then the runner will stop. And then another farmer comes up and prompts the child to stay focused back. So what we did with this game is we evaluated with 26 children with autism. I work with a clinic that is located in Tijuana that is called Pacitos. And so we compared a half of the children use Farmer Keeper and the other half use traditional cartoons, which is kind of the gold standard that neurologists kind of use. We also have a previous study that we use games, the games that they had, but the comparison was, we won, I mean, Farmer Keeper was higher in everything usability, so we ended up, going with cartoons as well. And then we conducted pre and post assessments of attention tests. These attention tests, the CRC, the ANT, and the ADHD are screening tests. So the psychologists, they use it to actually detect or diagnose attention deficit disorder. So the experimental group used Farmer Keeper and the control group used the cartoons, and they conducted 3 activity blocks of 4 minutes each with 1 minute of rest between these activity blocks. And they completed 13 sessions of neurofeedback throughout 3 months. So the therapy was given to them twice a week. So the first results that we have in terms kind of more in adoption. So you can see in the cartoons or the control group, the eye tracking data, it was scattered all the interface against the eye tracking or the attention children focus on the Farmer Keeper. this is one participant. Some participants also were looking at the score or up here. And this is huge, as we discuss with neurologists and neuropsychologists, as they say, like when when your eye travels or your brain, travels among different stimuli, that is not attention, what you're working is working memory. So it's so important. This shows how important it is. We spend so much time designing this game. How did you add widgets into the interface, and what areas of the brain they are going to promote the work on? So this is the result of the CRCD-AND test. And as you can see in blue, you can see the control group, or those participants who just sent cartoons. And on the orange side, you can see farmer keeper. And as you can see, both the students in both conditions improved their attention. But the students or the participants that used farmer keeper, their attention was, the improvement was double than the one in cartoons, and this result was significant. But what is also interesting to note is that these red lines, this red line shows a neurotypical, what is the attention score of a neurotypical patient. And as you can see, most of the participants from the farmer keeper study no longer have an atypical score. Some of the participants in the control group as well, but farmer keepers were higher. So this means, this is super huge, because this means that even though at the beginning of the intervention, these participants have an atypical score, so meaning they might have ADH or attention deficit disorder in addition of autism. And now, after 13 weeks of use or 13 sessions of use of farmer keeper, they no longer have an atypical score. And this is huge. And neurology says that the only thing that you can do this is that you can actually create or corrected the neural path in your brain. So we'll look at the EEG data. And as you can see, these are all the participants in each of the conditions, and there was no trend. So let's take, for example, participant 5 here, and as you can see, the attention was very low according to the threshold we defined, and then the second day increased. He stayed focused more time, and then reduce more, and then increase. And it was kind of the trend. And this is like, so I asked my student do a control test, and he actually conducted the 13 weeks, and it's kind of a similar trend. And we'll look at what happened in the cartoons, and the cartoons individuals were kind of the same. So what we learned about this project is, going back to our first question, can children with autism use their attention to control a video game? Maybe. I think we can, yes, as you can show, most of the participants use the game, finish the therapy. The problem was that by looking at the EEG data, I'm not sure if we are measuring attention. We also performed some correlations with the psychometric test. The correlation was non-existent or pretty low. So the problem here is that I really did not know if we are measuring attention. The signals we are measuring from the brain are currently very noisy. So we do have open opportunities there to actually understand more what's going on in our brain. The other thing what we learn is attention is a complex concept. It is highly contextual and depends on the workload. So like I said, as you can see in the EEG, so perhaps it was not related to the system. So perhaps it was related to what's going on in their house or on that particular day, and they couldn't be focused. And so this means that we need to use adaptive algorithms that will take into account the context of the participants. And the other thing I talk about, that what neurology said to us, like you create a new neural path or you corrected a neural path, and it will be cool if we can actually have a tool that can actually measure neural connections without having them to do an MRI. So the second project that I would like to talk of you today is to understand how the haptic interactions that we have with rigid touch-based interactions, what is the effect on our brain, and if we can, uncover digital markers. So one of the problems of diagnosis of autism is that we do not know the biological markers or the digital markers. And that's a huge problem because if we don't know that, we don't know how to treat it and we don't know how to diagnose it. So there's been recent developments in uncovering digital markers, and they have focused mostly on the major symptoms of autism, which will be like social interaction. So there's a lot about eye tracking or how they use their voice, and they have found that they do have an atypical tone of voice or pitch or voice, and also the way they move their eyes. But interestingly, there are very few projects that have tried to understand what is the difference or the typicalities in terms of motor development and also tactile processing, even though tactile processing is one of the first senses that it develops at early age. And also, like 80% of autism have a sensory processing disorder, and most of that is related to the tactile processing. So you will see here in this video an example of a child with autism that has sensory processing problems. They are either hypersensitive or hypersensitive to sound. And the problem is that their brain cannot absorb or integrate all the stimuli in our environment like our brain does.
Let's go.
So they result in having like this outburst, in public or when they feel overstimulated. So what we ask ourselves here is, can we measure alterations in tactile processing of children with autism using their interaction with haptic interfaces? So we developed, following a user-centered design methodology, a mobile haptic game that matches vibrotactile patterns to touch-based interactions. This game follows the metaphor of spiders, that spiders can feel vibrations on their legs. And the goal of the narrative of the game is to help a hungry spider to create a web and then eat bugs. And it kind of mimics a story in the nursery rhyme, Itsy Bitsy Spider. So the first interaction that we have is the tap. And we associated a gesture or a tap gesture or interaction to a vibrotactile pattern. For illustrative purposes, you will hear the pattern, but because you cannot feel it, but this is how it sounds. So a flat pattern, it is like just one vibration at one time, and we change the duration of that vibration. I'm sorry, like so. So in this activity, children must tap anywhere on the screen, and then what the activity is going to do is that a spider will feel the web. So on each tap, either on the spider or on the entire screen, the spider will move and will create the web, and that sound will be the vibration children will feel. The next activity uses the drag gesture, and it associates the drag gesture to a ramp pattern of vibration. A ramp pattern of vibration changes the intensity of the pitch, like so. So the idea is for children to drag the leg of the spider so they can grab the bug that fell on the web.
Mientras sientes la vibración.
And we have a final activity which is not that structured, that is open-ended, and they can either tap or drag, and the spider will dance on the web and eat bugs. So we collected data from 69 neurotypical children and 14 children with autism using feel and touch. And then we split it in the data sets that you see on the table. What's very interesting is that we use a screening test to avoid confound effects in the population. So we asked psychologists to do this test with the neurotypicals. And we tested against risk of autism, motor delay, and sensory difficulties. And as you can see, our 69 neurotypicals ended up being 43 because the rest, they didn't got a typical score on these neurodevelopmental disorders. And this shows like a clear example of the reality of the diagnosis and the problem of detection of these neuromental disorders in Mexico. So these are typical children. They are attending to a traditional school, and parents don't even know that they have this problem. What is interesting to see here is that we are categorizing interactions. So we ended up having this amount of data for each of the population we studied. So what we found here, we found 8 new digital markers that are not reported in the literature, and this is what is not published yet. But for illustrative purposes, I only have 2 here today. So the first thing that we found different is the amplitude of the vibration when children touch the screen. So when you do a tap or the US slide, the vibration that it means is different. So children with autism, that vibration is higher. And it's very interesting that it's associated to, vibration, which is something which is the stimulus that the child were getting. And the second biomarker we found is that the radius of the gesture, which is the size of the touch, for neurotypicals is smaller. So we used this data to train and test several machine learning models, and we ended up choosing the random forest who yielded the best results. And we were able to classify children with autism gestures against those of neurotypicals with 96% of precision. I don't have time to discuss more results, I'm sorry. So what we learned about this project is, can haptic interactions reveal new digital markers? And we think yes. I think that part of, that is biotactile stimulation is huge and, affects our tactile or sensory processing system and affects how our brain perceives tactile stimulation or tactile processing. So it will affect the way we interact with touch-based interactions. And that is why, the difference between neurotypicals and children with autism are huge, because children with autism are not able to typically process this information. Touch-based interactions and tactile processing has been widely underutilized. So if you dive into the digital marker literature, you will see a lot of movement and voice and eye tracking, but touch interactions are completely, there are 2 papers, one in Nature and the other one in Scientific Reports, to be honest. And they are not looking into this. I think one of the biggest problems is that physicians do not know that they can measure this data. So they do not look at tactile processing because right now they don't have data to measure it. But I think, this information is so important to use in tandem to the rest of the battery of screening tools that is used to detect autism. So what we want to do is, can we alter the surface perception by, altering characteristics of the biotactile pattern to uncover more digital markers? And of course, beyond digital markers, can we uncover digital phenotypes that can be used for patient and disease trajectory? So the final project I would like to discuss with you today is exactly along those directions. So there's some evidence in the neuroscience literature that we can trick our brain. So we're using that to change the perceptibility of your body. So interactive sonification has been used for this purpose. So interactive sonification is the use of acoustic signals as an output mechanism of an innovative natural user interface to provide feedback to the user. So as you can see in the image or in this example, if you are practicing the reach forward kind of movement, you can associate it to a bunch of sounds, structures, or musical structures like so. Like this is like a flat sound structure, and this is like a wave tone feedback. And the notes are arranged differently. This is like a upscale and downscale here. And that gives you feedback of the length of your movement. I wish I would give you an example in a minute. So as you can see, if you miss a point in the music, it feels like you haven't finished, right? You haven't finished the movement. So this is what interactive sonification is trying to do. But there's one particular very interesting characteristic of the use of sound that it calls the Pinocchio effect. And so the Pinocchio effect says that if we can manipulate the sound parameters, if we can change the pitch of the amplitude of the timbre, individuals their brain will be tricked, and it can alter their body perception. Like they might feel they are more like flexible or not flexible, and so on. So what we wanted to do is exactly that. Can we trick their brain? So we ask ourselves, can pitch variation alter our flexibility perception? So we ended up testing this in a yoga scenario, and we studied different movements of yoga, and we ended up choosing vinyasa, and we uncover like this analogy of the vinyasa cycles with the ocean waves, and we ended up designing sounds for the ocean. So we defined 3 particular sounds. So the first sound, so we use sounds from waist up in the upper lip movements, like wind sounds or birds that are, you know, on top of the ocean. And for those movements on the down part from your waist, we use water sounds. So for the step forward and back forward movement, we use submerged sound like so. And from the standing and flex, we use a wave movement. And then for the movements that are, you know, upper limb, we use wind movement. Sound. So that will be the normal pitch. And then we change the pitch. We alter for each of the sounds, we alter the pitch of the sound. This will be an ascending pitch of the same sound of the wind. And this will be a descending pitch. So this is a demo that shows all the vinyasa cycle and with the sound. We just connect at that time. We just connect. Now we're using OpenCV that allows you to use any camera. Okay, so that's how it works. So we conducted 2 studies. So the first study was to understand the effect of sonification in the subjective experience of a yoga class. So 40 novice yogis were randomly distributed in a group using sense or listening to these sounds against another group just listening to the teacher instructions. And the second study was a repeat measurement study, and we wanted to expose expose to all participants to all different pitch variations of the sound and see if this alters their perception of their flexibility. So these are the results for the first study. So what we found out is that the score of subjective experience for sounds, for the participants who use our sounds, was significantly higher. This means that they prefer to use the sounds while practicing yoga. And the second study showed also significantly that 50% of our participants had a higher perception of flexibility when using the ascending variation compared to the descending variation. So this means that, yes, we actually change the way they perceive based on the sound being used. So what we learned from this project is, can we trick our brain altering sound? Like, yes, of course, there was a lot of literature saying that, but in this particular scenario for flexibility perception or body perception, it does gives it does, confuses your brain very surprising. The variation of sound structures involve multiple factors. So here I just present a change altering the pitch. So, but we can alter duration, timbre, frequency. So there are a bunch of open questions of, how can we develop the sound structure or musical structures and combination and altered combination of these parameters, and what is the effect on our perception, our body. And so we're doing more about what is the relationship to movement and perception, and can we alter beyond movement abilities? I show you like an ability, can we alter movement qualities? And if it is a relationship between movement qualities and senses. So I don't have time for this exercise. So the takeaways of this talk, even though if you did not understand or stay focused during the talk, what I want to learn from it are these three things today. The first one, I think, this is a very new or exciting topic to work on. Neuroscience-based interaction could become a major healthcare trend. And current open questions are more related to, can we manipulate that stimuli available in natural user interfaces and alter sensory receptors like the last project that I showed you? And what does it mean to use this stimuli? What is the effect that it has in our brain? What the other, which is more related, is what is the effect of innovative interactions in our brain? Like I said, it's so important because these interactions are not there. So clinicians or the world does not know that we can measure these and that these interactions are changing the way we interact. And that has an effect on the brain, and there's a bunch of opportunities to study that. And finally, how can we measure those alterations in our brain? I show you, this example of measuring digital markers. Well, can we measure digital phenotypes, or can we measure actually neural paths or neural connections? And although the talk has kind of this flavor of moving from passive sensing to measure neuroscience-based interactions, because they are not widely explored, I think in passive sensing, this passive sensing literature also has a lot of potential to work into this area. So that will be all. Thank you. I would like to, it takes a village to do this type of research. So I would like to thank all of my students and my collaborations. And well, thank you. And I'll be happy to take your questions.
Thank you, Monica. Thank you for this very intriguing presentation. It opens really the field, I think, to a lot of questions. I'm going to wait if someone wants to start. Just please open your microphone and start. Otherwise, in the meantime, I have one question that from the beginning of your talk, it create me some, disturbed me a little. Then I understood it during the talk, what you were referring to. And now at the end, it again can, I don't know, you show very interesting and a lot of potential things that can enable a lot of the research that we do in positive. But when you said that we can manipulate stimuli affecting our brain, that immediately you show it at the beginning, puts me kind of a flag, right? Because you were saying it's possible to alter our perceptions and to create inconsistencies. What do you think about this from an ethical point of view? And if this research you are doing or we could be doing in this UBCOM field could need really to go hand by hand with some other kind of research more on ethics and these other aspects?
Yeah, that's a very interesting question and huge. And, you know, I didn't focus on that part, but at the very end, we need to be highly aware that we are talking here we are working with real patients with real problems. And the main idea is we are here to help. So yes, it could be understood wrong as I want to trick your brain, but what we are using it is we want to trick your brain to give you a benefit. So say, for example, if you are in a rehabilitation and you had an injury and you've been in a cast, and then somebody removed your cast, you are afraid to move your hand or your arm. So what we're doing here is, can we alter your brain so you know that you can push, you know, a little bit more? Or in a sport, it's how it is. It's how world records are still being beat. So that's what we are trying to do here. So what we want to do is to trick your brain to your own benefit, to show you that you have a better capability, or do you have a capability to develop a specific abilities. So that's a positive thing. At the beginning of my talk, what I'm saying is that what we are doing is altering a brain negatively, and that's a fact. So the fact that we give to our babies sensors and touch-based interactions at a very early age, where neuroplasticity is still happening, where the neural paths are being created, it changes their brain. So it's a huge responsibility. What I'm saying is that we have overlooked it, and we are developing extra games and video games and more stimuli, right? So let's do visual stimuli and let's add haptics there, and let's then add sounds, and that's a lot of a stimuli, and that it changes the way we are creating our baby's brain. So yes, next generations are different. So some of the examples that I will show you of the things that we're doing, the attention span of individuals is shorter, and also the intellectual coefficient, it's less. So this means that we are more intelligent than our children. And most of these things are being attributed to the technology and to the lack of capabilities we are giving them to focus on one task at a time. So they are exposed to so many stimuli that they cannot be focused for more than 1 minute, and that's huge. So what I'm saying, yes, it's a problem, and I started motivating my talk like that. What I'm saying is, like, we need to be very careful when we do so. Like I said with the Farmer Keeper, the first version of the game, it has a bunch of stuff. It has several animals, and it has several abilities to unlock animals and to catch animals, and a time bar in the right. And we get to the neuropsychologist and neurologist office, and they say, like, no, get rid of all that stimuli. I just want one thing in the game. You cannot have that many stimuli. That it will work a different part of your brain. So it got us thinking, like, they don't like, teachers, neurologists, clinicians, they don't like that many stimuli because the sensory processing system gets confused. So this is like thinking and, you know, design technologies that take into account this problem. So yes, it is kind of both. So what we're using is we're tricking our brain in a positive way, you know, for you to get a benefit. But yeah, there are others that if we don't take into account this, then we are changing the brain, and we need to be aware of that.
Yeah, very interesting. Perhaps it's also a matter of running longer trials, like randomized controlled trials, to prove actual efficacy of this in a way to actually expose children to the right interventions, right, in the longer term, to prove that this works really in positive. So having controlled trials might be the next step. Yeah.
Yeah, I think part of the pervasive healthcare community and tools that we are using is that we do very small pilots, and if we really want, to doctors, not this is very new, but more traditional kind of down to earth technologies, more like what you guys are doing in mental health, or Fitbit activity trackers and all that. If we really want doctors to start prescribing these things, we need to get pharmacological companies interested in that and get FDA approved and move into a clinical trial phase to show this is something that is going. Like with the Feel and Touch project, I think we are getting there. Like the dream is, can you be like, we only need like kind of like 1 minute or 2 minutes of interaction. Can you be at the pediatrician office, and while you are waiting, interact with this game, and then when you meet your pediatrician, like say, hey, the way your baby interacted with this interface seems atypical or seems more likely by a neurodivergent individual. And so if we really want to have accessible healthcare, like I said, and not ending in jail or lying to people, we need to run clinical trials, involve pharmacologicals, and move and doing that. Yeah.
Yes,
totally
and
agree.
go to the digital therapeutics workshop in Ubicon.
Yeah.
Other questions, please.
Hello. Thanks for the talk. I'm wondering about your first experiment that you presented. So if I understood correctly, you observed a significant improvement in attention, but you were not sure if you actually created some new neural patterns. So if you didn't, what do you think happened then? And how could you test this, what actually happened?
That's a very good question. And that's what we ask to neurologists. So what I say is, I don't have evidence to show you that we created a new neural path or that we corrected a neural path that was not there. But what neurology said to us is that actually happened. So when you conduct like an assessment test, and these are assessment and these are screening tools, and the HDHD, I didn't present it because it goes in the other direction and might confuse you guys. These are detection tests. So these are the type of tests that neurologists use to diagnose attention deficit disorder. So the test, the way that it works, it is like a discrimination test kind of. So I show you like different colors, and you have to pick the one that is red or the one that is green, and then I trick you with different things, right? And so what happened, it's like half of the participants, after 13 use of Farmer Keeper, they no longer had an atypical test. So I was so thrilled when we got that result, and I said, like, did we cure them? Kind of, right? That's what we want. So the HDH test shows you have attention deficit disorder, and then after 13 weeks, you no longer have attention deficit disorder. That's huge. So I asked them, how can this be possible? Like I have never had a result like this one. And they said the only way that is possible is that you created the right path, or whatever right means, right? Right in terms of neurotypical. We don't even know that, or paths are the right ones, but whatever, that's a different discussion. So you created that path, or you corrected one. But the problem that I have is I don't have how to measure it. I should be, those to measure that, children I must do an MRI, and with this, experimental interventions, I'm not going to ask them to use an MRI for me to measure that exact time. So that was my point exactly. The only way that you can, from a typical score, get a typical score and maintain that typical score after a while is to create that path. In every neurologist, I have presented several projects. This is not the only project that I will work with them. And they said, on each of the technology that you're currently using, this is what you guys are doing. You don't know how to measure it. We don't know how to measure it. We only have the MRI, but this is what you're doing. Yeah.
Okay, thanks.
Other questions, please. And see other questions coming also in the chat. So be brave, be courageous, and you have unique chance now. So let's give you 2 minutes, not 2 minutes, just maybe
to process all the information. I know it's difficult.
Yeah. If not questions come, then I think we will need to stop here. Okay, so still you're invited to interrupt me at any time, anybody, if you want another questions. Otherwise, I just again wanted to thank you, Monica, for this presentation. I think it was very stimulating to hear you and to hear what you guys are doing. Also, you said now that maybe would be too much asking for doing an MRI for someone, but if this works, really it works. it works doing that because well, it's having more evidence about this, even from some imaging or some other techniques, would be very interesting. Yeah, I don't see any other questions, so I thank you again for the presentation, Monica. Hope to see you soon in Ubicomp, and good luck for the conference. And yeah, we will be in touch, and thanks for being part of this WideHealth project in this presentation. Okay.
Thank you, guys. Thanks for having me. And, like I said, I applaud your effort. And if you have further questions or anything, please just email me and I'll be happy to chat with you.
We will.
Thank you. Bye-bye.
Thanks a lot, Monica.
Nice to see you all.
Nice to see you.